right, question number 6 asks you about high and low energy phosphate compounds. So it starts off by asking you to explain why ATP is a high energy compound. Well, there are 3 reasons why ATP is a high energy compound. All right, the first one is simple electrostatics. So each of the phosphates that we're bringing next to one another, each of these phosphates that we're bringing next to one another, carries a negative charge to it, right? And basically, the negative charge on one of these doesn't want to be next to the negative charge on the other. So they're repelling one another. So there's a driving force basically for one of these phosphates to fall off, right? So electrostatic repulsion is the first reason. All right, now the second reason has to deal with resonance. So when we have a phosphodiester bond, I guess I'll draw the oxygens here. All right, so when we have this phosphodiester bond shown here, right, this bond basically has a number of different resonance forms. So the lone pairs of electrons on the oxygen here can push themselves around and up onto the double bond oxygen like this, or alternatively they could move over in this direction like that. All right, well, what we have here is basically 2 resonance forms that are competing for the same lone pair of electrons. Basically we can have an either or but not both in terms of resonances. But if on the other hand, this was now cleaved, where we have 2 different phosphates, each with an oxygen with their own lone pair of electrons on them. Well, now we can draw that same resonance form, but for both of these. So there's an increase in resonance when we cleave the phosphodiester bond. Right. Now the last part that I'm going to talk about here, and I'm going to do kind of a superficial treatment of it, but hopefully the point will be communicated anyway, is that the phosphodiester bond here, when it is hydrolyzed, is able to be solvated better. Right? You can very simply think about this in terms of, when we have this phosphodiester bond, there's limited space available in these regions here. So it's relatively hard for water molecules to come and form a hydrogen bond with this oxygen. Now, once this bond has been cleaved, right, now I'm drawing them really close together here, but this phosphate could go off on its merry way here. It is very easy for both of these phosphates to get solvated. So there's increased hydrogen bonding or solvation potential here when ATP is cleaved. All right, and anytime we can form bonds, we're going to be releasing energy and basically stabilizing the products then. All right, so the 3 reasons why ATP is a high energy compound are, first of all, electrostatic repulsion, secondly, increased solvation energy of the products, and thirdly, increased resonance of the products. Now, part A here asks, why are PP and 1,3-bisphosphoglycerate higher energy compounds? Well, the answer is different in both of these cases, but the answer, the fundamental answer is that after cleavage, there's an extra benefit that comes afterwards that ATP doesn't even have. So in the case of 1,3-bisphosphoglycerate, we're just going to show the business end of the molecule here. All right, so we have this carboxylate phosphate here at the top of the 1,3-bisphosphoglycerate. Now, right now, the lone pairs of electrons on this oxygen here are being shared, this way, but also, with resonance this way. All right, so this is again a fairly unstable sort of situation. Now, the added benefit that 1,3-bisphosphoglycerate has is that when we cleave this bond, we now have phosphate, but we also end up forming a carboxylic acid. And the resonance of a carboxylic acid is a very, very nice resonance structure. And so because of this, we're basically stabilizing an extremely favorable resonance structure on the carboxylic acid or carboxylate. And this is giving 1,3-bisphosphoglycerate more energy than even ATP does. Now, for our last example, for phosphoenol pyruvate, let's draw it real quick. All right, phosphoenol pyruvate has an extra energy storage in that right now this molecule is basically trapped in an enol form. Now, enol forms always want to tautomerize to the keto form, where basically we push electrons down from the alcohol, forming a ketone, and then the alkene bonds get pushed over to the carbon and get protonated. But in this case, they can't, because we have this phosphate on there that we can't simply just remove with a base, for instance. We can't simply deprotonate this oxygen here. All right, but once the phosphate has been cleaved off, right, now we have this negatively charged oxygen here. We have our deprotonated enol species, which can then very easily tautomerize like so. An H plus there, giving us then the final product. And this tautomerization reaction, the equilibrium for this lies extremely towards the keto form, giving us this extra energy boost with phosphoenol pyruvate. All right. Now, the last question here has to deal with glucose 6-phosphate. Why doesn't it have as much energy as ATP? Well, let's look at where the phosphate is on glucose 6-phosphate. All right, well, to start with, all right, let's think about what we've got here. Let me draw these. All right, let's think about what are our three reasons why ATP was a high energy compound. First of all, we had electrostatic repulsion. Well, in the case of glucose 6-phosphate, we have a single phosphate group on it. The rest of the molecule is uncharged. So because of that, there's basically no electrostatic repulsion here for glucose 6-phosphate. So that's one of our reasons gone. All right, what about shared resonance of the bridging electrons? Well, in this case, the lone pairs of electrons on the bridging oxygen here can only be pushed up in one direction. All right, so there's already no sharing of resonance here for the lone pairs of electrons on the bridging oxygen. So that's also gone. All right. Now, what about other factors here? All right. Well, the other factor we talked about was this space in the middle here, above and below the bridging oxygens here, kind of surrounding the bridging oxygen, and basically making it hard for water to come in here and solvate the oxygen. Now, it is still true that we do have these other groups here that are helping to make it difficult to solvate that bridging oxygen, but compared to, in the case of the phosphodiester, these groups here were both oxygen atoms, which are relatively large and bulky compared to a hydrogen atom. So it's actually a lot easier for water to get in here and solvate the precursor compound. So there's less energy that is gained in the case of glucose 6-phosphate in terms of the solvation of the product. So that is your answer for number 6.